Assalamualaikum and good day. In this video, I'm going to continue with the topic of magnetostatic field. This is the second part in EMT course. And today I'm going to focus on the introduction and Biot-Savart's law. Okay, first of all, let's take a look at the definition of the magnetostatic field. Okay, what I'm going to do now is quite similar to what I have done in the electrostatic field. Okay, where I'm going to take the definition of the magneto, where this magneto means only magnetic field. In electrostatic field, the field that involved is E and D. However, in magnetic field, the field involved is the magnetic field intensity with the symbol of H. Okay, while the second field is the magnetic field density with the symbol of B. Okay, so now the static bring the same meaning as in electrostatic, where it means independent of time. Okay, let's say I'm considering the magnetic field intensity, so it will be H, and I'm consider the Cartesian coordinate system. Okay, in magnetostatic field, we are going to use the same coordinate system as we learned in the electrostatic field, where previously we have three, the Cartesian, cylindrical, and the spherical. And you're going to use any of that based on the situation of your problem. Now we are going to look at the sources of our magnetostatic field. Okay, as in electrostatic field, the source is a stationary charge. How about the magnetostatic field? In magnetostatic field, the source for the field is a moving charge. If you still remember, the formula of the moving charge can be denoted by J equal to rho V U. Okay, and the other condition that we need to consider for these sources is U should be constant. In electromagnetic field, U is giving a different situation. Okay, so I want to write here a same charge, if it is stationary. What of the field that it will emit? Yes, it will emit the electrostatic field. Okay, but if it moves with constant velocity, it will produce a magnetostatic field. However, if when it moves, which involve the acceleration or deceleration, it will produce an electromagnetic field. Okay, so here, what I can conclude that U, okay, will give a different field. If it is a stationary, a charge will emit the electrostatic field. But if the U here is constant, it will produce a magnetostatic field. However, if this U involve acceleration and deceleration, it will produce the electromagnetic field. But in this topic, we are going to consider this only. Okay, the moving with constant velocity, since magnetostatic field is our topic now. Next, we will develop the model for our sources, where the sources is quite similar to what we have in the electrostatic field. Okay, the first model is filamentary current, or line charge. Okay, let's say this is my line charge. Okay, and the I is moving in this direction. As usual, we are going to take a sample from our line charge. Okay, as you can see here, the I is passing through our sample. So, to develop the model, I'm going to write I here. Okay, another thing is the length involved in our sample. Since the length involved is very small compared to the line charge, we will write it as a dl. And here we are going to consider the direction of I move in this line. So this will be our vector. And the unit for this one is ampere meter. Okay, the second source is a surface current. Okay, and I'm going to draw surface that quite similar to that I've drawn in electrostatic. Okay, here the I can be in any direction on this surface. Thus, I'm going to write as a JS. Okay, when now the charge movement is very critical. Okay, the direction of the charge is very critical. And you need to write S here because this S denote the surface current density. Okay, now we need to take a sample. Okay, as before, we know that the J will passing through our sample. So this is our JS. And another one is the area involved here. So this will be ds. And the unit is ampere meter as well due to this one. Okay, where gs is ampere per meter and ds meter square. The third source is the volume current. Okay, let's say we have a cylinder to represent our volume current. Okay, and we have J in this direction. Okay, now this J is our volume current density. or current density. That's why it's very important to put S if it is a surface current density as mentioned previously. Okay, because J and JS is two different things. Okay, as usual, we are going to take a sample. Okay, let's say this is our sample. Okay, and we can see that this J is passing through our sample. Okay, so this will be J, and the sample normally for the volume current or the volume, we are going to consider our sample is in a box. So this will give us dV. Okay, and again, the unit will be ampere meter due to this one. J here is ampere per meter square, and this dV is meter cube. Thus, it will give us ampere meter. So here we can conclude that I dl js ds j dv. So all these our source for magnetostatic field. Next, we will investigate. Okay, we will investigate the relationship of our sources and the field. Okay, I want to make a comparison with the electrostatic field. Okay, and what we are going to look in magnetostatic field. Okay, first recall in electrostatic field, we have rho v as our source. Okay, and the field is E. Okay, the relationship of this is using Coulomb's law. Okay, and the formula for this is dE equal to sample multiply with the unit vector over 4 pi epsilon r square. So I hope you still remember this equation. Okay, where this is when we write it as sample, so we denote this as dE. Okay, now in magnetostatic field, we have J as our source. Okay, why J? Because the source for the magnetostatic is a moving charge, and the field is H. J and H is connected using Biot-Savart law. Okay, the formula or the equation between the Coulomb's law and the Biot-Savart's law is quite similar. Okay, where dH is equal to the sample unit vector over 4 pi r squared. Can you spot the difference between this equation and this equation? Okay, yes. In electrostatic field, we have epsilon. And epsilon is not exist in Biot-Savart's law. Why? Because the epsilon is the material under static condition. Okay, so logically, this is a moving. So epsilon won't exist in magnetostatic field. Okay, so I'm going to write this equation in a proper representation. So now let's JV replace this word sample. Okay, and we have AR here. And we know that this one is a vector and our sample is in vector now, and this is a vector as well. So we need to use cross product. Okay, and this will be over 4 pi r square. So the difference between these two equations is, first, this one we use a simple multiplication. However, in Biot-Savart's law, we are going to use a cross product. Okay, and the second one, the epsilon is not exist in Biot-Savart's law. And here you can replace your JdV with I dl if the source is the line current, or you can replace J as ds if the source is a surface current. So that's all for this video. Thank you.